So today we're going to see how to apply artificial neural networks to unsupervised learning. That is, when we don't have some target values in our training data that we want to adjust, like class labels or something for regression. And I'm going to show one way of doing this with autoencoders. So I'm going to start by giving a brief idea about what are autoencoders, and then talk about different restrictions that we impose on the network in order to obtain useful representations of the data. So we can do that by trying to compress the inputs into lower dimensions, or using regularization or other adjustments to training in order to constrain how the network is going to represent the data. And then we're going to see some examples more in abstract, and in the second lecture I'm going to talk about the exercises that will include this. So before going into more details, just to give you the general idea. An autoencoder is a network that is trained to output the same thing that we input. So as long as you have data, you don't need labels, you can train the autoencoder. And the idea is that the network is going to transform the data into different representations inside the layers. We saw that is basically how an artificial neural network works, by chaining together these transformations. But once we present an example, for example, an image of a cat, we want the output to be as close as possible to the example that we presented as input. So we don't need any more labels, we can train the network like this. And we can consider the autoencoder to be composed of two parts. This first half is the encoder that will map the input into this latent representation, this hidden representation inside the network, that is going to be a function of what the input is like. But it also must allow the other part, the decoder, to map back from this representation to the original input. So we are joining together two parts, one that makes this transformation into the latent space, and the other that reconstructs the original data from this transformed representation. And this is how we train the autoencoder. But then we can split it apart and use the first part or the second part. We're going to see several applications. So basically, we are learning to retrieve X from some transformation G, which is the decoder, from another transformation F of X. And this, when we look at it like that, doesn't seem to be useful. Why do we want the cat if we already have the cat? But the idea is that we are doing this with the composition of two functions. One that can encode the data into this hidden representation, this F of X, and the other that can decode it back to the original representation. So we don't need any labels, we are using the input as the target, and we are learning these two functions. So the advantage here is that this latent representation can have some properties that we impose on the network. For example, it can have a lower dimension. We have an image that has a large number of pixels. We can compress it down to a smaller vector that will keep the information that is necessary to retrieve the image, if we have the appropriate decoder, but it can represent the image with a much smaller with bandwidth, or much smaller number of bytes, whatever. We can use this to capture structure in the data. That is, if there are things that are similar, they will be close together in this representation, in this latent space that we have here. We can use this to compress data, to convert unstructured data into more structured data where the vectors all have the same length, and so on. So what we need is to force the autoencoder to do something to the data. Note that if we have a network that simply copies from one part to the other, then we don't have anything useful. So the idea here is that we are training the network to output the same as the input, but we are forcing it to do something useful to the data before retrieving it. So we need some bottleneck here to force this useful representation, otherwise the network will just copy the values from one layer to the other, and this depends on what we want to do. So basically we want something that captures the structure of the data, or maybe provides good features for an additional step that we have. But we're going to see some examples of this in the exercises and the assignment here. So this is the basic idea of autoencoders. We are getting out the same as we put in, but we force the network to do something to the data, and then we can break the network apart and use one of the parts, for example the encoder, to convert the data into that more useful representation. Let's see some different types. A very intuitive type of autoencoder is the undercomplete autoencoder, where the dimension of the hidden representation, of this latent representation, is smaller than the dimension of the input and of course the output, because the output is the same as the input. So basically we are reducing the number of dimensions in our data. We are going to train the network to minimize this loss function that compares the original input, x, to the chaining of these two transformations. Fx is the encoding, and then g of fx is decoding back again. And basically we can use a loss function that penalizes the differences between these. But this fx will convert the input into a lower dimension. So if we were to do this in a linear way, this could be similar to principal component analysis, for example. It could be an analogous, not exactly the same, because principal component analysis imposes this constraint that the vectors must be orthogonal. But if we add simply linear transformations, this would be the general idea. We're going to transform into a lower dimension by selecting the vectors in a way that makes it easier to retrieve as much of the information as possible. However, we can create complex networks here, so we have arbitrarily powerful nonlinear transformations, which leads us to a much more powerful way of reducing the dimensionality while capturing the structure of the data. Because remember, the network must create this representation in a way that allows it to retrieve the data again as close as possible to the original. So that's what we are trying to make the network do. Now, there is a problem here again with overfitting, since we have this arbitrarily large power of doing nonlinear transformations. We can have a network so huge that it simply indexes the examples. For example, it knows the first example is example number 1, and then if it receives a value of 1 in the decoder, it produces the image. And then if it receives a value of 2, it produces another image, and so on. So the information ends up being all in the network itself and not in the representation that we are creating. So if you use a network that is too powerful as an autoencoder, you have again the overfitting problem. And one way of testing this is to train the network to reconstruct a training set, and then look at how well it reconstructs examples outside the training set. So you keep looking at the validation error, just like what we do with other examples, because from the perspective of the network, this looks like supervised learning. You have an input, you have a target, and you need to minimize the loss function. From our perspective, it's unsupervised learning because all we need is the data itself and not additional labels, so we can use this with any label. But the idea for training the network is the same. So even when you're doing training an autoencoder, always use this validation set to prevent this from happening, where the power of the autoencoder is too large, and so the representation starts losing information because you have more information simply stored on the network and not on the representation. This is a classical example, Mitchell's autoencoder. We talked about this in the first lecture. You have 8 different types of inputs. Each input has a dimension of 8, but it's a one-hot encoded. That means that all of the inputs are 0 except 1, which is 1. This is a general way which we use to represent different classes, like you did last week with the fashionist, for example. But we are putting this in a network that has a hidden layer with only 3 neurons, and then the output has again 8 neurons that must match the same as the input. So the network is forced to create a more compact representation here, and what it does is basically learn these 8 combinations of zeros and ones, which is a binary representation of the 8 inputs. So this is very useful for manifold learning. This is just a brief review because we talked about this last semester. If you have something that is in a higher dimensional space, and you can create a lower dimensional representation that is homeomorphic, that one, there's a typo there, to an Euclidean space, meaning that locally it is similar to an Euclidean space. Even if you go to greater distances, it may not be. For example, a map is similar to an Euclidean space when you are around a location, but at the edges of the map, you cannot bend things in 2 dimensions, so it doesn't work that well. But this would be the example, turning the surface of the Earth into a 2-dimensional map would be an example of looking at the manifold, or if you have some kind of distribution of the data, even though this is in 3 dimensions, you can see that there is a 1-dimensional path through these points that could capture the relations between the points. So this would be the ideas that you can do with ISOMAP and TSNE that we saw last semester, but you can also do with autoencoders and try to learn these representations. So this is an example of a data set that has 4 dimensions, and if we do, these are 4 features that are taken from scans of banknotes to distinguish real banknotes from fake banknotes. If we want to visualize data in 4 dimensions, we cannot do it, but we can use, for example, principal component analysis to project these into the 2 vectors that have the largest variance of the data. And this would be the result. Here you can see the 2 classes, but they are quite overlapped because now we are choosing just one plane that preserves most of the variance and projecting everything there. If we use an autoencoder, for example this one, this is a simple multi-layer perceptron, so it's a fully connected feed-forward network. But the first layer has 6 neurons, then 4, 2, 4, 6 again, and then 4 at the end just to reproduce the inputs. And this forces a representation in 2 dimensions in the middle of the network. We are training the network to output the same as the input, but now we can use just this first part, the encoder, to convert the 4-dimensional data into a 2-dimensional representation. And here you can see that the structure of the data was much better captured, and we can see the difference between the classes. One important thing to note is that I'm using the class labels to plot this representation, but they are not used in the network. So the network doesn't care about the classes, it's just creating a representation of the data that makes it easier to retrieve the complete 4-dimensional data from this 2-dimensional representation. And that in itself is enough to organize the data in a way that makes these class differences very apparent. So this works basically because we are forcing the network to do 2 different things. Reconstruct the original data, but fulfill some constraints that we are imposing. For example, it must encode the data in a lower dimension. This undercompleteness is one way of doing this. We're going to see some other examples, but then just remember you must be careful to avoid overfitting. If we have a very large network, then the whole network can store the desired necessary information to reconstruct the examples in the training set, and then the representation itself may become useless because it doesn't matter what it is, the network can always learn some way of retrieving the data. One way of spotting this problem is, as usual, looking outside the training set to see if the network can reconstruct. Another approach is to use a different autoencoder that is not undercomplete. It may even be overcomplete. It may have more neurons in the hidden representation than there are dimensions in the input. But of course, to do something useful with this, we need to impose some constraint on how this representation is done. So we can use regularization, which are all those methods that change the way the model is trained, and there we can impose different constraints. For example, in a sparse autoencoder, we add to the loss function a function that will try to reduce or to approach the activation of the neurons in the hidden layer to some pre-specified probability distribution. So suppose that we want the probability of a neuron being active in the hidden layer to be this p, and this would be the average of the activations of all the neurons in the hidden layer. So we can compute the probability or estimate the probability of being active when we average the activations in the hidden layer. And what we can do now is, in addition to the loss function, where we compare the output of the network to the input, so that we are reconstructing as well as possible the input data, we also add this measure of the divergence between the actual activations that we are measuring on the hidden layer, so this average activations on the hidden layer, and a probability that we specify with which we want the neurons to be active. For example, let's say we want only 10% of the neurons to be active for each example. We can use 0.1 there on P, and now we're going to measure how much the actual number of neurons firing is diverging from this probability. And this, the Kullback-Leibler divergence is often used here. This is basically a measure of how probability distributions diverge. So we add this as a regularization term, and now the training of the network will try to minimize the reconstruction loss, the difference between the input and the output, and with some weight that we can adjust, the divergence between the activation of the neurons in the hidden layer and some probability that we are specifying. So this means that the network, even though it can have many neurons in the hidden layer, it's going to try to activate only a few of them for each example. And this will lead the neurons to specialize in those features that distinguish between the examples. So here is one representation of the kinds of patterns in an image that lead to an increased activation of each of the neurons in the hidden layer of this sparse autoencoder. And we can see that they are being specialized for different kinds of contrasts and angles in the lines that appear in the image and so on. So by forcing the network to fire only a few neurons for each example, we make the neurons specialized in different things that are important to distinguish the example. And even though we have many neurons, we have their useful representation of specific features the examples may have. So this is also an example here where they have trained the sparse autoencoder on the MNIST dataset. This is a dataset of handwritten digits, the one that we're going to use today. And you can see that the specialization, as we go, if we don't use any penalty for the training, so we are not forcing the regularization on this autoencoder, results are not very good, but as we increase the kind of penalties we impose for regularization, we can see that the neurons are becoming specialized to patterns that are clearly similar to parts of the numbers, to parts of those lines. So this way, even though the hidden representation can have a larger dimension, we can specialize the neurons into giving us useful information about the patterns they find there. Another way of training autoencoders, which can be implemented in parallel with any of the others, is the denoising autoencoders, where we force the autoencoder to give us the original data, but we input in the autoencoder the data corrupted in some way. For example, we add noise to the data, and then we force the autoencoder to denoise the data to bring back the original image. And this effectively forces the autoencoder to learn relations between the elements of the input that allow it to discard the noise and understand, so to speak, what the input should be. So we can even train this to then apply to new images and reduce noise or things like that. But this is also a form of regularization where we are, by inputting noise, we are presenting these examples changed to the network. Yes.
Is it going to distinguish between what is noise and what is not noise? Or?
Yes, because you have the original image. We have this image. And we want the autoencoder to output this image. So we are going to measure the error with respect to this image. But we don't present this image to the autoencoder. We first scramble some pixels and present that with the noise. So we are going to train the autoencoder to figure out what is the noise we are introducing, because it must approximate not what we are giving it, but what we want the image to be, which is the original one. So of course, if we put too much noise, or if it doesn't have enough images, it won't learn properly, but the idea is that it will learn to distinguish noise from the original. So basically the algorithm here is when we take an example from our training set, we apply some kind of corruption with some probability of noise, and then we train in order to minimize the difference between the output and the original example that we got, not the noisy version. A contractive autoencoder is a different, another alternative here, where we again add a regularization term to the loss function. So this is the difference between the output and the input, and this regularization term is some scaling factor multiplied by the sum of the magnitude of all the partial derivatives of the output of the encoder with respect to the input. So basically, we are penalizing the encoder when it becomes too responsive to small changes in the input. And we are making the autoencoder, or the hidden representation, be more robust or less sensitive to those changes in the input. So this tends to encode similar examples grouped together, because if there are small variations between one example and the other, the autoencoder will try to reduce the encoder's sensitivity to those small variations. And this is basically why it's called contractive, because it tries to squeeze together the representations of similar examples. It also favors smaller weights here, so this is has an additional effect of reducing the danger of overfitting. But basically the idea is that we are trying to make the encoding less sensitive to small perturbations in the input, and structured in a way that similar examples are forced to be grouped together. This is related to denoising autoencoder. So basically the denoising autoencoder also results in an encoding that is less sensitive to small perturbations, because the autoencoder needs to learn how to ignore those noise values. And sometimes the denoising variant is easier to train, because the contractive autoencoder, this part, computing all of these partial derivatives when you have high dimensional data, can be expensive and takes longer to train. So one cheaper alternative to this could be to use a denoising autoencoder that gives you a similar result. This is just a comparison of the kinds of patterns that different neurons are being specialized to respond to when we use a contractive autoencoder, and when we look at the importance of different pixels in PCA, for example. So you can see that here with the contractive autoencoder we are responding to much more meaningful attributes of the data, and basically things like PCA are not very good for manifold learning, because PCA only cares about the variance in different dimensions and not so much the structure of the data itself. We can also create stochastic autoencoders that learn in the hidden representation probability distributions. And then the decoder will basically sample from those distributions. Here we can use different distributions, but I'm going to give an example of this with variational autoencoders that allow us to generate data. So one thing that we can use autoencoders for is if we have this mapping from the input to the latent representation, we can use the encoder part to create an encoding of our data. But since we have this mapping from this representation here to the space where the original data is, we can in theory generate new data like the one we have if we choose the appropriate values here in the encoder. So the autoencoder not only gives us the encoder but also gives us the decoder that we can use if we know how to pick values in the hidden representation. So this latent representation that is created from the data could then be sampled if we pick some point here in this latent representation that corresponds to something useful, like the original data, then we could just feed that into the decoder and obtain, for example, a cat image of a different cat in this case. And this is a difference between a model that is merely discriminative, which is a model that tries to give us an approximation of a conditional probability of some example with features X having some value, some target value of Y, for example, belonging to a class. An example of this is logistic regression, where we are explicitly trying to find this conditional probability. And this is called a discriminative model because it only allows us to tell if the example belongs to that class or not, or if it has that value or not, or the probability given the features of having that value. But it doesn't allow us to go back. So if we say, suppose an example belongs to class 1, what would be its features? This model cannot tell us that because it only learned the conditional probability from the features to the class. A generative model approximates the joint probability distribution of the target values and the features. So we can do it both ways. If we have the features, we can estimate the probability of being in some particular class, for example. But if we have the class, we can have the probability distributions of the features and thus generate. So with autoencoders, we could do this, but if we decode from the hidden layer, we have basically this conditional probability. Given the features of the hidden layer, we can output something that would be like the data we want. But we also need to know what is the distribution there in the hidden layer in order to be able to generate data from the autoencoder. So basically, if we try to sample and we hit the right part of the latent space, we have something that is meaningful. But if we fall outside the right part, we have something that is garbage, because this is no longer the kind of things that the network can convert into the data that we want. So we need to know what is the distribution here in the hidden layer, in the hidden representation, in order to be able to sample from there examples that are meaningful. So one way of doing this is to use generative adversarial networks. We are going to say that the latent space has some fixed distribution. For example, Gaussian noise on all of these neurons. And as we start with this kind of decoder architecture, but before training, this only produces rubbish. And we want it to produce, for example, cat images. But what we can do now is to train another network that takes images like this and is trained to classify them in either fake images produced by the other network or real images which are part of the dataset that we have. So we can train this network by generating a set of images with the generative network, and then the classifier network takes in all of these images and tells us these ones are fake, this one is real. So in the beginning, this is very easy because the other network only produces rubbish, and this one easily distinguishes between the two. But now we're going to train this network not only to produce images that make the other network confused, that make the other network classify as true images. So basically the loss function for training the generative network is how to best deceive the discriminative network. And then the discriminative network is trained alternating with the generative network. And this is why they're called generative adversarial networks. We are using them to generate the data, and they are being trained adversarially. As one improves in the quality of generating the data, the other needs to also improve in the way of discriminating between them. So this has progressed a lot through the years, and in the beginning there were some experiments in creating faces, for example, but nowadays the faces look very realistic, and it's very easy to generate faces of fictional people by the generative adversarial networks that have been trained, one to generate images and the other to decide if it's the face of a real person or if it's a fake image generated by the network. So this is one way of solving the problem of figuring out the distribution of the latent space, which is basically to fix that distribution and train the decoder in order to give us the right results. One other approach is the variational autoencoder. So what we're going to do is to train the encoder to tell us the parameters of the probability distribution with which we have to sample the decoder to get something similar to that of the input. So this is the idea here. We're going to add to the loss function the difference between the input and the output. We're going to add this term, which is the Kullback-Leibler divergence between the probability distribution that is generated by the encoder and some probability distribution we want it to be like. And now the thing is, how can we say that the encoder is generating a probability distribution? We could in theory sample lots of examples from the encoder and figure out what the probability distribution is. But for the variational autoencoder, instead of doing that, which would be computationally expensive, we don't actually sample these probability distributions. We have the encoder tell us what the probability distribution is. So this is the idea of the variational autoencoder. The encoder takes in an example of the data and then produces in, for example here in two different dimensions, the parameters of a probability distribution. In this case, we usually use Gaussian distribution, so we have a mean and a standard deviation. So this would be probability distribution 1, we need two values, the mean and the standard deviation. This would be the other one, also with two values. And now, to put in the decoder and to train everything, in this step, we are going to randomly sample these distributions and feed the result into these neurons. So this would take this mean and standard deviation, we sample at random, feed into this neuron, do the same thing with the other one, and then obtain some output here, and we use backpropagation to adjust all the weights here. So this is the idea. We have the encoder learn probability parameters of probability distributions with which we can then compare to our desire. We want independent Gaussian distributions, for example, and we must try to juggle these two things, minimize the difference between the output and the input, and also give us these distributions as close as possible to what we want. The question here is, how do we backpropagate through this part? Because remember that backpropagation uses all those derivatives with respect to the parameters. And if we have a step here where we take a random sample from this distribution, we cannot compute the derivatives because this is a random sample. It's not a deterministic function. So this requires this reparameterization. Suppose that the value that we are putting here on the decoder, so this value that enters here, is simply the mean value here plus the standard deviation multiplied by something. So this part here is deterministic. It's the mean plus the standard deviation multiplied by something, and we can backpropagate here because the derivative here will be that something, the value that we happen to multiply by. This value, the something that we multiply, is a random value chosen with the normal distribution of 0 mean and 1 standard deviation. So this reparameterization gives us the Gaussian distribution there with the parameters. We cannot do backpropagation here because this part was randomly sampled. But it doesn't matter because there are no parameters here. This was just a random toss of the dice, and we don't care because the network continues from this side. So using this reparameterization trick, it's possible to train a variational autoencoder using that part where we are sampling from probability distributions, but still we can backpropagate the derivatives of the error through all the parameters that we need. And one interesting thing is when we combine those constraints on the probability distributions that we had here, when we combine them with some information about different classes and different types of examples, we can force the variational autoencoder to disassemble or to separate different aspects of the data. For example, this is trained with the NIST dataset, which are these handwritten digits. And the two neurons in the representation were forced to tell us about different aspects of the data. So one of them, depending on how we sample the distributions there, or how we change the parameters of the distribution in that neuron, tells us what number is going to be written. And the other determines the style in which the number is going to be written. So we can have these combinations of having, for example, a very thin one, or a thicker one, or one that is vertical or more slanted, something like that, and the same for other numbers. We can combine the style and the content by picking different probability distributions on those neurons. And the same here with the faces. It's not as clear with these small images, but the idea is the same. We have different styles and different people with the same haircut or glasses or things like that. So we can basically deconvolute the different aspects of the data, and then by choosing the right parameters on the encoding, we can generate images that have this particular style with this particular content and so on. We can use autoencoders, the same principle, with convolutions entering and then convolutions leaving again. So many of the examples I presented here with images would be like this. You use convolutions in and out to reconstruct an image. What we need to do to implement this is this part you already know. We use convolution and pooling to shrink the size of the feature maps, and then we can add more filters so that eventually the representation that we have here is less sensitive to the position of patterns on the image, but identifies different elements. But now we need to be able to do the reverse. So basically, convolution, the reverse is just another convolution because that is a linear kernel that you're passing through the data, and you can easily learn to do the opposite just by passing a linear kernel with different parameters. But we also need these steps of upsampling that are reversing what pooling has done. There are different ways of doing this, like transposed convolutions and things like that, but the one that works best is just to take your feature map, upsample it, for example, with interpolation or with nearest neighbor or something like that. We are copying values or interpolating values, and then we apply another convolution. And the convolution will, let's say, focus better the image that we are getting here with the transformations it's going to learn to do. So this is a simple implementation. It's easy to do this. We have the encoding part where we do convolutions and pooling, and then we do the same convolutions and upsampling instead of pooling in the reverse order. And we are creating the decoder that is going to learn to undo what the encoder did. And then we can have a useful representation there, or use this for other things. One example is deep fakes. So one problem here is that we want to replace, for example, the face of a person with the face of a new person. We can generate images of that other person if we know the distribution of the latent space and we have the appropriate decoder. But the problem now is how do we create an encoded representation of the image of the first person in a way that we can then generate an image of the second person. And the answer for that is to use a shared latent space where both encoders can point to. So we're going to train the same encoder for all the faces. For example, here we have John Oliver and Jimmy Fallon. We can add noise in this example. They make some distortions to the face so that we can effectively increase the training data and force the encoder to learn to fix small problems in the pose, in the position of the face, and so on. But we are using the same encoder, and we are training two autoencoders. One uses this encoder to encode the images of Jimmy Fallon into this latent space, and then this decoder A for Jimmy Fallon to output the same image, but without the distortion. So it's also a denoising autoencoder. And we do the same with John Oliver images, but we use a different decoder when training with John Oliver. However, we are using the same encoder. So this representation, hidden representation, is basically the same. We just have two decoders that are specialized in producing either John Oliver or Jimmy Fallon images here. And now what we can do is to combine these differently. So we input image from Jimmy Fallon to the encoder, but then we use the John Oliver decoder and we get a replacement of the faces there. So this is one way where we can learn a shared representation space and use that to sample the correct images with the appropriate decoder. Okay, so to sum up, the idea of the autoencoders is that we are just learning to output the input, which means we don't need additional labels, but the trick now is in what we do inside the network. So we impose constraints either by reducing dimensions, by regularization, and all of these tricks that we can use, adding noise and so on. And we can use this not only to create good representations of the data using the encoder, but also if we figure out how to learn the distribution of these latent representations, either by, for example, fixing the probability distribution with generative adversarial networks, learning the parameters with variational autoencoders, using shared encoders and different decoders and so on, we can then use this to generate examples similar to those that we have.